So now we start lecture 9 of the helicopter dynamics course, and today I am going to discuss the spring mass damper system, which is a cornerstone in structural dynamics. I'm Dr. Ranjan Ganguly. So in the previous lecture we discussed about the spring mass system and we basically neglected damping. Now that is okay for some systems, but in general damping is a real part of the physical world, and therefore for typical engineering systems we cannot neglect damping. So one of the simplest models of a damping force is Fd is Cx dot. So this is the time derivative of x, and this is sometimes known as a viscous damping model. And it is the simplest model which we can add to the spring mass damper system, and it is quite realistic in many cases and gives us a lot of insight into the structural dynamics of a typical system. So here there is a mass suspended by a spring K, and here we have a damper. The damper has damping C. So if we were to pull this mass and then release it, then some forces are going to act on this mass. We are going to have Kx, which is the restoring force by the spring. We are going to have Cx dot, which is the restoring force by the damper. And then there is going to be mx double dot, the inertia force, which acts counter to the direction x or reverse to the direction x. So it acts in this direction. So the net result of these three forces is that we can write the governing equation mx double dot plus cx dot plus kx equal to 0, because there is no forcing on this problem. This is again a free vibration problem. We are going to discuss forcing in a later lecture. So that's our governing differential equation, mx double dot plus cx dot plus kx equal to 0, which is ubiquitous in structural dynamics. So to solve it, we assume x is est, where s is a constant. We substitute it into this equation. Now, if we were to differentiate this once, we get s est. If we differentiate it twice, we get s square est. So we put it into the differential equation here, we get this characteristic equation. Now here est is not going to be equal to 0 at all times because it's an exponential function. Therefore, this must be 0. In fact, est cannot be 0. So this must be 0. So we can then write this in this form here by dividing throughout by m. So we get s square plus c by ms plus k by m equal to 0. That's the characteristic equation. Now once we have got the characteristic equation, we can solve this. It is a simple quadratic in S, and therefore we will have two roots, and they are going to be negative c by 2m plus minus square root of c by 2m square minus k by m. So that's a big equation, and what we are going to do is we are going to try to simplify this nomenclature by expressing things in non-dimensional form. You already see some of these things are simple. K by m could be replaced by natural frequency square, but we are also going to find some better way to write c by 2m. And to do that, we define something known as critical damping. And this is basically defined in this form. So we can say Cc by 2m is K by m, this thing being squared. And at the point where this holds, that point is known as critical damping. And this essentially is coming from the square root term we discussed in the previous slide. Now, at this particular damping point Cc, we can write Cc is 2m root k by m from this equation by taking the square root of both sides, and therefore this also becomes 2m into the undamped natural frequency of the system. So interestingly, Cc is a property which you can obtain if you know m and k. It really does not depend on C itself, which is very interesting. So from this we now discuss one more term, which is the damping ratio, that is C by Cc. And C is the damping of the system, Cc is the critical damping of the system, and in most cases we discuss vibration in terms of damping ratio rather than taking the absolute value of damping C. So let's get back to our characteristic equation here and try to look at these terms. So C by 2m could be written as C by Cc into Cc by 2m, and C by Cc is zeta, the damping ratio. Cc by 2m is the natural frequency of the non-damped system. Similarly, K by m is the natural frequency of the undamped system square. So by using these two definitions, we can write this whole thing in a simpler form, and we'll be able to extract the natural frequency out of this whole system. So if we do that, this is our first equation here. From here we extract this omega n term, and then we take this term out completely here, expressing this entire term in terms of the damping ratio zeta inside the brackets. So the roots of the characteristic equation S12 can be completely given by this. Now the behavior of this system is going to depend on the values of zeta. So three values are of great interest. One is zeta less than 1, one is zeta greater than 1, and the third is zeta equal to 1. So you can clearly see if zeta equal to 1, you have the critical damping case. That's the borderline. So let's first look at zeta less than 1, which is the most interesting case, and this is what is often typically known as vibration. So this is also sometimes known as the underdamped case. So here we write x in this form. Now recall that since zeta is less than 1, these are becoming imaginary numbers. So I is coming here, I being root of -1. So this is the expression here. You can rewrite it into form of sine and cosine, with which we are more comfortable in the physical world. So essentially this is the solution of this governing differential equation for the spring mass damper system. Now at the first point, if you were to set zeta equal to 0 here, this term would become 1, and this term would become 1, and this term would become 1. So you would get C1 sine natural frequency t plus C2 cos natural frequency t, which is the solution for the spring mass system without the damper. So that's the first check we should do on any system, is that once you have derived it, you set some of the terms equal to 0, and you should get back the previous simpler system. Now sometimes we write this in this form where you have an amplitude and a phase. Some people are more comfortable with this notation. So here again you can check that if zeta is 0, you would get x sine natural frequency time plus phi, which is the solution of a spring mass system or simple harmonic motion. Now essentially, if you think, there are two aspects you can figure out from these equations, how the equation talks back to you. One is that you have to find either C1 and C2, two constants, or you have to find x and phi. So these are certain things we need to find. And for that, we need initial conditions. So just like we discussed in our previous lecture, x0, x dot 0, or some values at some different point need to be known. And you can then calculate C1 and C2, or you can calculate x and phi. Now the damped frequency is one more concept, that is essentially the natural frequency without damping into root 1 minus zeta square. You can also write this as 2 pi by tau d, that is the damped time period. Now you can see that if zeta is 0, these are same, but also if zeta is very small, such as 0.05, they are going to be nearly same, and that is what we meant, that in many cases if damping is small, the undamped natural frequency is sufficiently good and you can use it in many cases. But if damping were to become large, like zeta is 0.15 or zero point 0.2, then you need to consider the damped frequency here. Remember, the damped frequency is in terms of radian per second, and tau d of course is in terms of second. So this is a circular frequency. Let us now pictorially look at these three types of motion. So let's start with zeta less than 1. This is the vibratory motion. So you can picturize this graph by looking at this equation here. If we were to set time equal to 0, we would get x sine term would be 0. So we would get x sine phi, this term being 0. So that's where this graph starts from, x sine phi, and then it continues like this. So it decays because of the presence of this exponential term outside. So you have the xe minus zeta natural frequency t, and this is the decay of the term, and the frequency of this motion is the damped frequency. So it is root 1 minus zeta square into omega n. The second important case is zeta greater than 1, and this is the overdamped case. So in this case, zeta greater than 1, both the roots s1 and s2 of the characteristic function or characteristic polynomial are real, and so this is our solution. Now here the solutions are pure exponential, so there is no going back to the sinusoidal realm here, and therefore you are going to get exponential terms. You are not going to get an oscillatory motion, and the motion will decrease exponential with time, and it's known as an aperiodic motion. So that's what the motion looks like. Essentially, it's a sum of the motion of the two exponential functions. One of the exponential functions is coming down like this, second one like this, and the total is coming like this. So that's the basic concept in this particular problem. Now the third case is critical damping, and that is zeta is 1. That is at the borderland of these two damping scenarios. So here you have S1 is S2 is this particular value here. Now if we were to set zeta is 1, this would vanish. So you would essentially get two repeated roots. Both the roots are same. And if you go back and look at the theory of differential equations in any math book such as Krejcik or something like that, you will find that when you have repeated roots, you get a peculiar type of solution. So the solution would be x is a plus bt e minus natural frequency of the undamped system into time. This is the solution here. There is an exponential decay, there is a time into exponential decay. So this looks something like this here. It's a critically damped system. It's at the border of the undamped system and the overdamped system. And therefore, this is a point where the oscillatory motion switches to the non-periodic motion. So that's the turning point here. So of course, what is most important for practical purposes are the cases zeta is less than 1, because that's the case which takes place in most real world and physical systems, and that's the case we are going to be most interested in. So again, I will see you in my next lecture where we'll continue this study on helicopter dynamics and review of structural dynamics to prepare the groundwork for the course.